Welcome to How Machine Learning Works. I'm your host, Gary Chan. I'll open with a brief bio on myself, then we'll talk about artificial intelligence, or AI for short, versus machine learning, or ML for short. Then we'll cover the different components of a machine learning solution, and then have a sampling of different machine learning algorithms. I've structured this content to be conceptual in nature. Machine learning is extremely heavy in mathematics, so I've included some basic math to provide a fuller understanding. My name is Gary Chan, and I specialize in anti-fraud, information security, and machine learning. I have a bachelor's from MIT in electrical engineering and computer science, as well as multiple security certifications. I'm an entrepreneur building a machine learning product and a mentor for cybersecurity startups. I've led a number of different organizations and teams to handle anti-fraud and information security challenges. Let's start with the difference between artificial intelligence and machine learning. I've heard the terms used quite interchangeably and often incorrectly. Machine learning is a subset of artificial intelligence, which means that every machine learning solution is also an artificial intelligence solution. But not all artificial intelligence solutions are machine learning solutions. So what's the difference? Machine learning changes its decision-making process based on experience. In other words, it learns. You and I each have a resume that represents past experiences that we've had, such as prior jobs or past education. Those experiences have affected how we think and the decisions that we make. For that reason, we are machine learning machines. Artificial intelligence is a superset. Artificial intelligence may or may not change based on experience. We're going to talk about machine learning because that's where all the hype is, and frankly, it's a lot more interesting than just artificial intelligence. So why should you care about machine learning? For starters, machine learning is ubiquitous. It's used everywhere. Amazon uses it to recommend products for you to purchase, and Zillow uses it to estimate home prices. Machine learning could replace you. I don't mean all of you. I mean certain aspects of what you do on your job. Machines are very good at specific types of tasks, and they are also more efficient, accurate, and cheaper than you are. After this video, you may wish to hire a machine learning expert to provide a competitive advantage for your business. And if none of these reasons convince you, consider that machine learning silently influences you. If you use a modern app to read news, for example, that machine is showing you news articles that are personalized to your preferences. That can create bias in what you read or watch because the app has decided what to show you. Machine learning can be used to make your life better or worse. So what are the components of machine learning? I'm sure you can find a number of different frameworks on the internet that explain this in a different way, but I've chosen the one that I think would make the most sense to IT professionals. Features. That's the first component of machine learning. Suppose that I want to purchase a house. What are the features that I might care about? They could be, for example, the square footage of the house, the number of bedrooms, or the school district that the house is in. These are the features that I care about. The second component of machine learning is data. Knowing what features I care about is not very useful if I don't have the data showing me the different houses that are for sale along with their features. The data is an essential part of machine learning. The third element are the algorithms. How do I think about the list of houses that I have and the features that I want in order to prioritize and select the houses that I want to look at and potentially purchase? This algorithm is what I use to determine which house I want to purchase. The fourth component is the platform. For you and me, that's the human body, because that's where the algorithms are stored. For a machine, that could be a robot, or it could be a server in the cloud or on my laptop. It could refer to the operating system. It's the hardware and software that the machine is on. And these are the four components of machine learning. Today, we're going to focus on algorithms because that's the meat of machine learning and also probably the element that IT professionals are least familiar with. This slide shows a number of different machine learning algorithms. This is not intended to be an exhaustive list, but it is intended to share a large number of the most common machine learning algorithms, along with some of their relationships. Today, we'll focus on the algorithms on the right-hand side. We'll first talk about supervised versus unsupervised algorithms, and then we'll dig into supervised and talk about regression and classification algorithms. Then we'll go into unsupervised algorithms and cover clustering, anomaly detection, and recommender solutions. We are not going to dig deeper into reinforcement learning, neural networks and deep learning, or ensemble methods, but I'll briefly mention them here because you'll probably hear about these in the news. Reinforcement learning is most commonly used for things like autonomous vehicles and also for artificial intelligence in games. Neural networks and deep learning are used for very complex types of situations like facial recognition or perhaps trying to predict medical diseases. Ensemble methods is a fancy term to mean a combination of a lot of other algorithms. Let's start with the difference between supervised and unsupervised algorithms. Let's say that I'm trying to teach my fictitious son Jack the difference between a dog and a cat. I give him 100 photos of dogs and 100 photos of cats. These photos comprise the data that I give to Jack. At this point, I don't know what algorithm he is using to learn the difference between dogs and cats, but he is probably using different features in his algorithm, like the animal's ears or tails. By the end of the training period, and training is a machine learning term, Jack should have learned the difference between a dog and a cat. Now, let's say that I'm not a very good father, and I give Jack 200 photos of dogs and cats, but I don't tell him which photos are of dogs and which are of cats. I tell Jack to divide the photos into two groups. The hope is that Jack divides the photos between dogs and cats. He might get a few wrong since I never told him what a dog looks like or what a cat looks like. But that's the best case scenario. Since I never told him what features to look at in the data or what the categories to divide the pictures into were, he might divide the photos into something completely unexpected. He might divide them between dark-colored dogs and cats and light-colored dogs and cats. We don't know what features Jack used or what algorithm he applied to divide the pictures. We simply have no idea. In this case, we did not control the outcome of what Jack learned, and this is an example of an unsupervised algorithm. Now that you know the difference between supervised and unsupervised, let's dig into the first supervised algorithm. This algorithm is called regression. The question is, how many emails will I receive today? Let us assume that the number of emails I receive is a function of the number of days at the job. For instance, if I am very new to the job, then I should have very few emails. However, if I've been at the job for many years, then I should have many more emails. What do I do with this data? What I can do is guess that the number of emails that I get per day is a linear function of the number of days in the job. In other words, y equals theta 0 plus theta 1 times x. And for any given employee, if I know the number of days that he's on the job, I can guess that he will get the number of emails that is represented by this straight line. This straight line is pretty good for a large number of cases, but it's not perfect. For example, it will go off to a very large number over here that is simply not representative of what we're seeing for long tenured employees. So what can we do here? What we can do is try to find a better fitting equation. For example, we could use a quadratic formula with an x squared term, or a logarithmic formula with a log term. Either of these formulas will produce a green line such that you see in this photo here. So this is much better, and it's pretty good actually for all of the plots that are around the green line here. But we can also see that there are quite a number of examples that are far below the green line and examples that are above the green line. So what can we do here? We could also try adding more features. We initially assumed that the number of emails per day was a function of only the number of days on the job. Right here, what I've done is I've added another variable, the number of hours per week worked. So part-time employees, for example, those who work 20 hours per week, are represented by the green line here. Employees who are full-time, working 40 hours per week, are represented by the green line here. And then we also have employees that work a lot of overtime, those who work 60 hours per week, and those are represented by the line here. And by adding more features, we are now able to produce a better model showing the number of emails that an employee might receive. So where might you use regression algorithms? You can use them pretty much anywhere that you want to make a prediction of a continuous value. For example, home prices, or the number of sales that your company will have next quarter, or the stock market price. You could also try to predict the number of expected attacks on your firewall, the number of burglaries in an area, the amount of inventory loss you might suffer, or the amount of patient records that will be stolen during a breach. Insurance companies, for example, will use these to determine the premium that you will pay for your insurance. Let us cover a second common supervised algorithm called classification. The question is, can I classify my spam emails? Now, let us assume that we have a vocabulary list of spam words. So this list would include things like Viagra, or Nigerian prince, or pay now. And I count the number of words that are in this list in all of my emails, and I plot that along the horizontal axis here. I also have domain reputation, which is just a score between 1 and 100, and I'll plot them on the vertical axis. Then I place a B for any email that is bad, or a G for any email that I would consider to be good. And I place them here onto this graph. So then the question is, how do I divide up this graph so that I get all of the bad emails on one side and good emails on the other side? One thing I could do is to draw a straight line, y equals 1, or spam, if x1 plus x2 is greater than c. That's this green line right here. And on the right-hand side, I will have all of the bad emails, and on the left-hand side, hopefully, all of the good emails. Now, I can move this line to the right or to the left, but if I move it to the left, I'm going to get some of the good emails and mark them as bad. And if I move this to the right, then I may end up just getting more bad emails marked as good. So what are other things that I can do without changing the threshold? I could try a better fitting equation, like I did in the regression example. For this classification example, I could guess that y equals to 1, or spam, if x1 squared plus x2 squared is greater than c. And that equation draws this green circle here. So anything outside of this circle, I'll call a bad email, and anything inside of the circle, I'll call a good email. As you can see here, I've eliminated some of those other b's that were there when I had a straight line. So this is clearly a better equation. There is still, however, a single b that's here, and let's say that's unacceptable, and I want to continue optimizing my algorithm. So what can I do? Well, we could add more features. For example, we could add an SPF check. And in this example, the SPF check failed, and so I'm able to throw out that email and mark it as a bad email. And in this particular way, I've now classified all of my emails between good and bad. So what are some example use cases where classification is helpful? We could use classification to identify objects in pictures. We could use it to sort food. For example, if I owned a farm and I had a harvester that harvested a number of different types of food, I could use a machine learning algorithm to divide the different types of food into different bins. I could classify people by likely political affiliation, and that could help politicians, obviously, try to target specific groups of people for votes. It could also identify potential threats. For example, the TSA inside the airports could use facial recognition or other types of algorithms to classify people between potential threats and non-threats. We could identify friend or foe for automated weapon systems. And we could classify documents into specific known buckets like top secret, secret, etc. Let us start with our first unsupervised algorithm, clustering. The question is, where should I locate my hot dog stands? For the purposes of this example, let us assume that there are 3 hot dog stands, and we want to locate them in places that will maximize the amount of foot traffic. I have here a map of St. Louis County, as well as P's that represent people that are in those particular locations. Now, this is a very contrived example, so we can very easily see that the hot dog stands should probably be located in the center of each of these 3 clusters, where these P's are. Now, in reality, the P's would be all over the map, and it would be very difficult for us to determine where the hot dog stands are. But it would not be difficult for a computer at all. It would just have to follow the algorithm and iterate through it. So let's talk about what the algorithm might do. The first thing that the computer will do is randomly pick 3 starting locations. These 3 starting locations are called mu1, mu2, and mu3, and these are our centroids. For each of these centroids, we're now going to color each of these P's the color of the centroid that is closest to it. So, for example, these P's right here are very close to the mu1, and so we're going to color those red. And these other P's are closer to the yellow mu2 than they are to the red mu1, so we're going to color those yellow. So let's do that now. Once we do that, the next thing we want to do is we want to move the centroids to the center of the colored P's. So, for example, the red mu1 will be moved to the center of this cluster of red P's, and the yellow mu2 will move to the cluster of the 3 yellow P's. And now we're going to iterate by coloring the P's the color of the nearest centroid. So, for example, here we're going to recolor these red P's to be yellow. And then now we're going to move the centroids to the center of the same colored P's. And we can see here, after a couple of iterations, the computer has determined the location for the hot dog stands. mu1, mu2, and mu3. So where might we use clustering? We could use it to segment customers. So marketers will often segment customers by age or by gender, for example. A machine learning algorithm that is not told exactly how to segment the customers might come up with a very good segmentation that marketers never thought of. That segmentation might be some combination of age and gender, or it might include other features that the marketer never even thought of. We could use it to identify the optimum t-shirt sizes. So let us assume that I have a company that makes t-shirts, small, medium, and large. If I know the people that I'm selling to, I could use this algorithm to determine the optimum sizes in inches, for example, of the width of the shirts that I want to create so that the maximum number of people will have well-fitting t-shirts. We could use clustering to pick fantasy baseball players. We could also group documents into arbitrary buckets. Now, I use this example specifically to contrast with the earlier example of classification. So if you recall, the earlier use case was to use classification to group documents into known buckets like top secret or secret. That was because we knew what buckets we wanted at that time for classification. In this clustering example, I'm not telling the algorithm what buckets to use. So it might bucket them into completely different buckets, like all documents that talk about cats or dogs. And that could be very useful if I have a number of documents and want to group them, but don't know exactly what groupings make the most sense. I could use clustering to identify high crime locations in a city, or I could use it to find friends of known criminals. So let's talk about another machine learning algorithm that is unsupervised. This is called anomaly detection. And the question is my Exchange server compromised? So let us assume that I own a data center and I have a number of Exchange servers. And I've taken the data and I look at the number of emails that are sent today and the number of logins today on the server. And I plot them on this graph here. What I will then do is look at it and say, well, which one of these, if any, are anomalies? So how do I do that? What we could do is assume a Gaussian distribution model, or a normal curve, also known as a bell curve that you might remember from high school. And on this plot, they show up as rings. And these are going to be my probability rings. So I can say that anything that's in the center here, anything within the green, is very probably normal. And anything that goes a little further out is less likely to be normal. And then I've set a threshold so that anything that is outside of this red area is noted as an anomaly. In this particular example, I have one anomaly. So in this case, the algorithm will throw an alert to the analyst, and the analyst will look at the anomaly and determine whether or not the Exchange server was compromised. So let us assume that in this particular case that the analyst said, no, this was not a compromised Exchange server. This is absolutely normal. So what could we do about that if we wanted to improve this model? Just like in the other examples, we could try a different distribution model. So for example, we could try something other than a Gaussian model. So we don't use concentric rings, for example. We could use some other distribution model that might be triangles, for example. We could also try adding more features. One very interesting thing about this is that anomaly detection problems often become classification problems. And this occurs when there are enough examples of the anomaly. So let us say that in this instance, the analyst said, well, the Exchange server was not compromised, but what happened is that it ran out of disk space. If we have a lot of anomalies that show up like this, and in every case it was because there was disk space shortage, then this is no longer an anomaly problem. Instead, we should be using a classification algorithm to identify when our servers are running low on space. So what are some examples of anomaly detection? We could use it to detect abnormal airplane engine behavior. We could use it to predict whether a hard drive is about to fail, or to detect motion. We could find intruders both physically and digitally, detect fraud, or detect fake reviews. These are all examples of anomaly detection. So let us look at a third and final example of unsupervised learning algorithms. This is a recommender algorithm. And the question is, how does Netflix recommend what I watch? So I have here a table that shows about 5 movies and 4 people. And these 4 people, Abby, Bob, Charlie, and Denise, have each rated 3 or 4 movies on this list. And the ratings go from 1 to 5, where 5 is a very good movie and 1 is a bad movie. So in this particular case, Abby watched Black Panther and Iron Man, as well as Titanic and Isn't It Romantic, but she did not watch Avengers Endgame. So the question is, what would Abby rate for Avengers Endgame? What would you guess for each of these ratings? What you might do is divide the movies between action movies and romance movies. And you'll notice that Abby really enjoys the Black Panther and Iron Man movies, which are action movies, and she doesn't enjoy the romance movies like Titanic or Isn't It Romantic. So you might guess that Abby would enjoy Avengers Endgame with a rating of 5. And then we can do the same thing with Bob for Iron Man. In this particular case, Bob really enjoyed Black Panther with a rating of 5 and enjoyed Avengers Endgame with a rating of 4. So it's a little bit unclear whether he would rate Iron Man as a 4 or as a 5. So in this instance, we might guess 4.5 just to split the difference. We would do the same thing with Charlie and Denise. So the question now is, can a computer do better? All right, remember that we are looking at 5 movies split between action movies and romance movies. What we could do is add action and romance into the table, and then evaluate each of these movies to determine how much of the movie is action and how much of the movie is romance. In this particular example, I've just created numbers. These may or may not reflect the actual division of the movies between action and romance. Again, it's just an example. Now, to fill out this table, we could do this manually. For example, I could hire a critic to watch each of these movies and then make the determination as to how much of the movie is action and how much of the movie is romance. I could use clever surveys, or I could use another machine learning algorithm. And in actuality, we would probably use another machine learning algorithm. Let us just assume that this data is available to us. Now, I can imagine that it would be fairly straightforward for a person to watch 5 movies and come up with some sort of division between action and romance, although it could be subjective. But imagine that I had a whole compendium of movies. Maybe I have 100,000 movies, or maybe even more. And I have not just 2 genres, action and romance, but I have 30. At that point, it would become increasingly difficult for a human, or even a team of humans, to do this. But it would be fairly trivial for a computer to do so. So what I'm demonstrating here is actually something that a computer can do, but which would be quite difficult for a human. So that's why in the prior example, the human just divided things between action and romance and did not attempt to do some sort of analysis of how much percentage is action and how much percentage is romance, because that's not very realistic for a human to be able to do across so many movie examples. But we can do it with a computer. So back to this example. What we can do is calculate the prediction ratings. So in this particular example, Abby really enjoyed Black Panther and Iron Man, and probably because those two had a very high percentage of action. If we look at her rating of Titanic, it had a small amount of action, and so she rated Titanic with a 2. Which is still a little bit more, though, than Isn't It Romantic, that had absolutely no action in it whatsoever. So we can say that Abby would probably like Avengers Endgame with a rating of 4 because it has 80% of the amount of action as Black Panther and Iron Man. We can do very similar calculations for Bob, Charlie, and Denise. Now let us compare what we thought the 4 people would rate the movies at, and that's on the left-hand side, with what the computer thinks the 4 people would rate the movies at. And we can see that the numbers that we predicted are different than the numbers that the computer predicted. In every case, the number that we predicted was different than what the computer predicted. And I would argue that the computer is a lot better. It's actually a lot more accurate because it's taking into account more precision and information than we did when we used just the high-level buckets of action and romance. So in this particular case, Abby is going to enjoy Avengers Endgame with a rating of 4, and we would have predicted 5. And this is why Amazon and Netflix are actually going to be far better at predicting what you will want to buy or watch than even your best friend or your spouse. So what are some example use cases for recommender machine learning algorithms? We've already stated the first one, which is products to purchase. We can use the algorithms to determine people to date, people to hire, movies to watch, or the best tool for a person based on his skill. So to recap, today we've gone over the difference between artificial intelligence and machine learning. We've talked about why one should care about machine learning. We talked about the 4 components that comprise a machine learning solution. And we covered 5 different machine learning algorithms in detail. We also covered a number of different use cases for each of those machine learning algorithms. So with that, I wanted to thank you for your time and wish you good luck in your studies.